Okay, so let's discuss the VI characteristics. Already we have discussed. So this in VI characteristics of your normal PN junction diode. Actually, we draw just 1 minute. This is the VI characteristics. If you take this is the current axis, forward current or a diode current in milliampere range, and this is the diode voltage, which is between the volt, and in the reverse direction we will have the reverse voltage, and this current will be having a very huge range from some micro to nano ampere. So this diode current here, it is in the range of microampere or nanoampere. So when we plot the characteristics here, like if it is the normal PN junction diode or it may be a silicon or germanium diode, so we got a characteristics like this. Okay, so after the threshold voltage or knee voltage, we got the significant amount of current here. Okay, so and in the reverse direction almost the current is very negligible, and it will enter into the breakdown after the breakdown voltage. This is basically the VI characteristics of this diode. So here one more thing we want to discuss here, that is the AC and DC resistance or diode resistance. Okay, so this diode resistance, what is this diode resistance, we will discuss. So obviously we are getting the relationship between your voltage and current. So directly the what we can say, we can directly got the resistance by dividing the voltage and current. Okay, so here we can see that the voltage and current are non-linearly related here. That's not a linear relations like your Ohm's law here. So the voltage and current, their non-linear relation is there. Okay, so we can find the resistance offered by the diode, because the diode is having some material, means obviously it is having some resistance. Also it is having some ohmic contact when we connect the diode. If this is the diode, like physical structure of the diode, we connect it through the metallic wire, so there must be some ohmic contact in both the side. So, and also the material properties, whatever the properties of the material, it offers some resistance. That's why we are some voltage also drop across this diode. So the what is the resistance across, or the resistance offered by the diode, that we have to need to determine. So in the when we see about the operation point of view, when we use the diode, so in some cases we may use the AC signal, in some cases we may use the DC signal. So according to the application of the diode may be connected to some DC signal, like 5 volt or 12 volt or 3 volt, 4 volt, whatever the requirement. And sometimes the diode may be connected to some AC signal. Some AC signal is also connected in the diode. So this is the AC notation, this is the DC notation. Okay, so when we apply the DC voltage, means a fixed voltage we are applying. So at this voltage, the resistance offered by the diode may be different, the voltage drop across the diode may be different. And when we offer the AC signal in the diode or AC voltage in the diode, in that case the resistance is different. So we can represent the resistance in both types, that is DC resistance. This DC resistance is also called as static resistance. Static resistance of the diode. So what is this? How it can be calculated, this DC or static resistance of the diode? When we consider about the VI characteristics, if this is the VI characteristics, it is not exactly this much. This type of graph we are having. This is the IT and this is your VT. So when we talk about the DC resistance or this static resistance of the diode, usually with the notation of this dynamic resistance or static resistance is capital R. We represent it as the capital R, or sometimes we can represent as the DC resistance directly RDC also we can write. So in this point directly, if suppose you have applied whatever the applied voltage 5 volt or 12 volt and you have a fixed operating point, means operating point means at which voltage the diode we are operating, so that is called as your operating point. Suppose at this point this is the amount of voltage applied, so at this voltage what is the current? Suppose this is a point A, let's say this is the origin O. So at this particular voltage, let's say V, what amount of current we are getting? That ratio, that is voltage by current, will be your static resistance or DC resistance of the diode. Means at a certain operating point, we will get the resistance, or one another way to find this resistance is that we will calculate the difference, or we join this origin point to this operating point. So this distance, that is OA, and this distance OB. So we can take this let's say this is the point OV, or this point name. So suppose this is a V volt. So let's say this point is suppose B. Okay. So we can take the ratio of this point, your this voltage, that is the ratio of this point, that is OA or OB by OA also we can take, or directly this sorry, not OB or not
AB.
Sorry.
AB.
Yes, I'm. Yeah, so we can have this change in your voltage by change in current also we can consider. So this relation we can take. This is the voltage, this is this one, and at this point, let's say this is, let's say, point B dash. So we can take this voltage by current, change in voltage from minimum point to your operating point, and change in your current also from minimum point to maximum point. So this we can take OB by OB dash. Let's say this is a B dash. In this way also we can find the static resistance of the diode. So this static resistance is actually, it is not having so much of importance in diode characteristics. So it's the study of your static resistance, or by knowing the static resistance, it will not so much of helpful in operating the diode, because it is a fixed quantity. But the dynamic resistance is having some significant role in diode analysis. So what is this AC resistance or this AC resistance? Or this is called as your dynamic resistance. It is usually represented as lowercase r, or sometimes it is represented as RD, dynamic resistance, or RAC also we can represent. So how to calculate this? When we apply a AC signal means it's a alternating current. So obviously, and there we have to consider the RMS value or average value we want to take directly, because AC current is not a fixed current. So we are having, when we apply the AC voltage, obviously the current will also change according to the applied voltage. So for calculating the AC resistance, we have to calculate the change in voltage with respect to change in current. So for that case, how to calculate this AC resistance? This R.
PR by DI.
Yeah, dV by DI. dV by DI. We want to check change in voltage with change in current. So how to find this change in voltage to change in current? So from graphically, from the graph only, from BI characteristics, if you want to find the, suppose the applied voltage or the operating point of that diode is at a certain point. Suppose this the same graph or one more graph we can take. So if we take this kind of, we are having this kind of graph. Suppose the operating point is here. So here the operating point means this will be the average point or average voltage you have to take. So at this point we will take a tangent, we draw a tangent, and at this point just make a triangle, and this change in, this will be your change in current, and this will be your change in voltage. This we can take del V or change in voltage by change in current we can take. Okay, also we can analytically we can find the AC resistance. So you know the relationship between your voltage and current of the diode, that is the diode equation. So from the diode equation, can you find this dynamic resistance? With the diode equation, just take the differentiation of your diode equation for finding the AC resistance. So we are having this diode voltage V is equal to, or Vd is equal to your I naught e to the power, what is that? I naught e to the power V by eta Vt
मैम isn't
minus
it
1.
ID?
मैं वो तो डायोड करंट होता है ना।
Sorry, diode current,
Yes.
diode current, ID. Yeah, ID is equal to I naught e to the power V by, this is actually the diode voltage, the same notation you should use. So Vd by eta Vt minus 1. Okay, so from this relationship we can find this change in your del I. Okay, change in del I with respect to your for finding this dynamic resistance, or try it to find this. Or approximately we can have this this equal to I naught e to the power Vd by eta Vt, na? Because this I naught is very smaller in comparison to ID, so we can neglect that also. So taking ID is equal to this much, we just differentiate this with respect to Vd and find the dynamic resistance.
Ma'am, eta Vt upon I naught e to the power Vd by eta Vt.
Yeah. So here we can differentiate it. So change, if you just take the differentiation, and for the forward biased case, if you find the value of your V by eta Vt, okay. So this is a assignment for you. From this I'm just giving the hints. Okay, just try yourself. So taking the differentiation and putting some approximation like B by eta Vt. Okay, this value is much more greater than 1. Okay, and I is much more greater than, or the diode current is much more greater than I naught. So with this approximation, at room temperature, what will be the dynamic resistance that you need to find? Okay, this is next class I will ask. You can follow the book also. So what will be the dynamic resistance? You just find it. Okay. So so always the diode will offer some resistance. So whenever we represent the diode by its equivalent circuit, this is an assignment for you. If you will not be able to analyze this one, then in the next class I will do it, but you just take some time and analyze this. Okay, actually this dynamic resistance we will get, that is Rd is equal to 26 millivolt by your diode current ID. This much you should obtain. Okay, so this value, and this value will be useful in many applications, many analysis we will use this. So how we are getting this Rd is equal to 26 millivolt by IT, that is up to you. You just find it. Otherwise in the next class we will I will discuss. So when, as we are now we are aware that the diode offers some resistance. So if you draw the equivalent circuit of a diode, equivalent circuit of diode. So if you draw a equivalent circuit for the diode, this is simply a diode, okay. It may be a silicon diode, or it may be a germanium diode, or any other type of diode. So if you represent the diode by its equivalent circuit, so its behavior can be understood. So from that circuit should behave like this diode. So we know this ideal diode is just a switch. Ideal diode is just a switch. uh, so as the diode is offering some resistance, we can represent some resistance also, okay. And before that we need to represent some voltage drop across the diode also, okay. Like if this is the diode, it is applied by some voltage, represented by some voltage with some resistance. So this will be your dynamic resistance RD. This will be the threshold voltage whatever the diode, across the diode we are getting, and this is the ideal diode, okay. So when the normal diode is just like a ideal diode. So can you just analyze in forward bias and reverse bias mode how this will be operating? So suppose we consider the forward biased case. So as we have discussed, in the forward biased case the diode behaves like a short circuit. So in the forward biased case we can replace the diode by a short circuit equivalent, a voltage source, and its dynamic resistance RD, okay. This is the equivalent in case of forward biased case. And in case of reverse biased case, if you consider the reverse biased case, then the diode will be replaced by open circuit, then there is a voltage and the dynamic resistance RD. So there is no mean of this circuit, because one open terminal is there, so the current will not flow through this, so there is no use of this. So in case of a reverse bias condition, we usually just remove the diode, or it will be just treated as an open circuit and the circuit will not work. In case of forward biased case, we are having the circuit equivalent is just the voltage, threshold voltage or the knee voltage, and the dynamic resistance of the diode. This is the diode equivalent circuit, we can say. So this diode equivalent circuit, it will be useful when we solve the circuits having diode. So usually when in some cases this RD, this diode resistance is a very smaller resistance in comparison to the load resistance or other resistance present in the circuit. So usually this RD is also not considered by when we solve the numerical, until and unless it is not specifically asked to use the dynamic resistance, okay. So we will solve some numerical so that it will be more clear how it will be treated, okay. So let us take some numerical. Okay. So question is, calculate the forward current. Calculate the forward current IF, okay, for silicon diode with dynamic resistance RD is equal to 0.25 ohm, and yeah, only the dynamic resistance is given in the following circuit. So here a circuit is given where one voltage is applied. Suppose this is 1.5 volt is applied here. This is R1 is equal to 10 ohm, it is applied, and a silicon diode is placed here. This is a silicon diode. This side is ground side. Okay, so here the applied voltage is 1.5 volt, dynamic resistance is given, and the resistance in the circuit, it is 10 ohm is given. So the voltage across the diode we need to find, so that we can find the current across the diode. So here the forward current means IF will flow through this. So as here the positive terminal of the applied voltage is connected to the P side of the diode, so diode is connected in the forward biased mode. So we have to find the current across the circuit, which is the current across the diode also. So directly we can have, how we can find the current? So we can find the just apply the Kirchhoff's voltage law. So for finding the current, so basically we what we will do, so if you apply the KVL, how to apply the KVL? So when we applying KVL 1.5, so whatever the voltage we are having here, so we are moving from negative terminal to positive terminal. So you have to maintain one direction, one polarity in always you have to consider the polarity how you are following. So negative to positive, usually we represent it as the positive, it is a general practice. So this is 1.5 volt minus the same current will flow through this circuit. So this IF into R1, so this IF into R1, and here the silicon diode is there. So silicon diode is, it can be replaced by is its 0.7 volt DC source and one dynamic resistance RD. Okay, and it is in the forward biased mode. So as we have seen that how this can be replaced by its equivalent circuit, so this silicon diode can be replaced by ideal diode. So this is the ideal diode, then it can be replaced by a voltage that is 0.7 volt, then one dynamic resistance RD, or the dynamic resistance whatever the value is given, and this is the applied voltage 1.5 volt. So in the forward biased condition, this diode can be replaced by a short circuit equivalent. So it is just like a short circuit equivalent. So now we are having the current IF in this loop. Okay, so this will be represented by, this is 1.5 volt minus IF into R1. Then here also the current is flowing, so this will be positive to negative. So this will be minus 0.7 volt. Okay, minus IF into RD, that is equal to 0. This is the loop equation. So from here we can get the value, that is your IF is equal to how much? IF will be equal to 1.5 volt minus 0.7 volt divided by your R1 plus RD. Okay, that is the resistance offered by the diode plus the resistance of the circuit whatever it is applied. Both the resistance we have to consider, and you have to just take the voltages. So if you find this value, how much we will get, just calculate the value.
78 milliampere.
Yeah, this is 78 milliampere. Yeah, either you can represent 0.078 ampere or 78 milliampere. So here the dynamic resistance of the diode we have considered. Okay, just you can see that the value it is given here, the resistance is 10 ohm. whereas this resistance is 0.25 ohm. So it is a very smaller resistance in comparison to the resistance used in the circuit or the load when the load is used. In this example, it is just to show the effect of this dynamic resistance. We have considered the dynamic resistance. So whenever the dynamic resistance is not mentioned, usually we just neglect that resistance also. So this is one type of numerical. Then let us see if two diodes are connected, how you to find the series voltage or parallel voltage, all these things. Just 2-3 examples we will do so that it will be more clear. One more numerical, find the voltage, find BA of the circuit given. Okay, so the circuit is given like this, like here it is given plus 15 volt. This is a silicon diode. Another silicon diode is here applied, and this is a VA. This is just 7 kilo ohm resistance is there. So for this circuit we have to find the voltage VA, or that is the basically the load resistance. 7 kilo ohm load is connected here. So this kind of connection, if it is given, just you for your information, just I have given this, that you should know how to understand this circuit. So whenever one terminal is given and one voltage is written, it means that it means that it is also a closed loop. It is just appearing as a open loop, but it is a closed loop. When we are just notation is given plus 15 volt, that means the circuit, it is given like this. This is the diode, okay, and this is the 7 kilo ohm resistor. And this circuit, it means that it is a 15 volt DC voltage is applied. So this positive terminal is connected to this point. This is the indication where plus 15 volt is written, means positive terminal of this voltage is connected to this point. So this is just similar way we can just connect this in this way. And this voltage with respect to ground, it is taken, okay. One voltage only it is written, means we cannot give in a single point we cannot provide the voltage. Obviously when we give the voltage, means two terminals are required. So one terminal is not given, in the sense it is with respect to ground it is given. So this is also connected to your ground terminal. This one is your ground terminal. So this is the circuit here. So this voltage BA, like here BA you need to calculate. BA means at this point we want to calculate the voltage. That means with respect to ground we have to calculate the voltage. That means voltage, this BA is this voltage. With respect to ground, this BA need to be calculated. So practically when you measure the voltage at a certain point, always we measuring the voltage means what? We measure the potential difference between 2 points. That is the voltage measurement, na? So when you put the voltmeter, when you use the voltmeter also, there are two terminals in the voltmeter. Okay, one will be your red color terminal, another will be your black color terminal. So usually we put the red color in the positive side and black color in the negative side, and we just measure the voltage. So the potential difference between 2 points the voltmeter will display. Okay, if you just reverse the polarity, black को हम लोग अगर positive side में और red को negative में लगा के अगर voltage measure करेंगे, then that same voltage will be appear as the minus of some volt, minus volt. So negative polarity we will get. So to get a proper voltage, usually it is a practice that is the indication of that color. Red color को हम लोग positive terminal में और higher potential में रखना है, black को lower potential में रखना है. So whenever it is given that at a particular point, if voltage is given, other point is not given, means with respect to ground that voltage need to be measured. So here this BA is this voltage across this 7 kilo ohm resistor is your BA. So this we need to calculate. So here there is no points here indication of your dynamic resistance. So we can just ignore that dynamic resistance part here. So it is because 7 kilo ohm resistor is connected here. So dynamic resistance will be very small resistance. It will be in the range of some milliohm or something. So it can be neglected. So it is not mentioned anything about the resistance, so you should ignore that resistance. So if you are ignoring that resistance, just see how it can be calculated. So if it is the positive terminal is connected to the P side of the diode, so both the diodes are forward biased, so it can be replaced by your equivalent voltage source. So equivalent voltage source means it is the silicon diode it is given. So this is positive, this is negative, this is positive, this is negative, this is 0.7 volt, this is 0.7 volt. So we can replace this by 0.7 volt and 0.7 volt. Now just apply the loop. So let's say current is your forward current, or simply I also we can take. So what will be the current I here? So just apply the KVL. So if you apply the Kirchhoff's voltage law, then negative to positive, plus 15 volt, this is positive to negative, minus 0.7 volt, this is positive to negative, minus 0.7 volt, this is with respect to this BA means this is the positive terminal, this is the negative terminal, so this will be minus I into 7 kilo ohm, that will be equal to 0, or directly this will be BA also we can say. Okay, so either I into 7 kilo or it is BA also we can write here. So what will be the VA, voltage across this VA?
13.6.
How much?
13.6.
13.6. Yeah, 13.6 volt. So in this question you need to calculate the BA. If required, you can calculate the current also. I will be equal to this BA value is your 13.6 volt divided by your 7 kilo. You can find the current value also. So the current will be I think it is
1.94 milliamp.
943 milliampere. So in this way you have to calculate this voltage or current in that diode. One more numerical just I will take. So suppose your question is in this way it is given. The circuit is given like this. Like one silicon diode is given. This is the silicon diode. One germanium diode is given. Germanium diode. So it just connection is like this. So here one resistance, 1 kilo ohm resistance is given, and here the voltage applied is your, this is your ground terminal. So this is your V output voltage. So this is positive, this is negative, and your applied voltage is suppose here plus minus 10 volt. Okay, so here the current is, let's say I. So here you have to determine the output voltage V out kitna hai, and what will be the current for the circuit. What will be the I current for this circuit. Okay, so
in is equals to 9.79.
when
9.7.
which one, voltage or current?
9.79 VO, ma'am.
V output, yeah, 9.7 voltage, and current
9.
yeah, voltage is your 9.7 volt, and current how much? How much current?
9.7
Milliampere. Yeah. So here you just see that both the diode are forward biased. Okay. So the silicon is replaced by 0.7 volt. Okay, 0.7 volt, and germanium is replaced by 0.3 volt. Okay, so obviously the germanium diode is activated when 0.3 volt will reach. So obviously this path will not be utilized by this circuit. So this path, the path of the circuit will be in this way you have to consider. So the lower voltage drop across this path. So we consider this 0.3 volt and apply the loop. So this will be 10 volt minus 0.3 volt minus V naught is equal to 0. So with that loop we can find the value. So this will be your.
Ma'am, so the circuit won't even consider silicon even no.
Yeah, because with less voltage drop the path is getting na. So low resistance path it is getting. So high resistance path will not be used.
Entirely, ma'am. No parallel formula will be used.
No, 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 not required. Because
Thank you.
if it is getting a low resistance path, then current will not pass through that high resistance path. Okay, so in the next class, we will discuss about the diode capacitance and the load line and operating point of the diode. After that, the general characteristics of diode will be over, then we will switch over towards the application part of the diode. Okay.
Ma'am, please share this one today, ma'am.
Sure, sure, sure. Just now I am sharing.
Share the slides. And ma'am, attach.
Excuse me, ma'am.
Yes.
Ma'am, yesterday in the second half, I